So Jeff's going to take you through a technical, what are you calling your presentation?
A technical voyage.
Okay, yeah, a journey. We're going to, hopefully help you understand a little more about what it is we do and how we do it. Some of you might wonder why we're actually doing this and why we're so active in the market, sharing our IP and sharing the technology. And at the end of the day, it's because we have a lot of passion for this market and this particular style of facade. I recognized 15 years ago when I started with it, nobody really knew how to apply it in our market. And the biggest challenge is these are European design products. They're lightweight and they're meant to be hung on a certain way in Europe, where they use these aluminum profiles and then bolt them to the concrete wall and rivet the panels or screw the panels or backhang the panels, and it generally works. But in the Canadian market, we build with steel studs, 18 gauge, 6-inch steel studs, and most of the walls that we're attaching to are not concrete, they're light gauge metal studs. So what ends up happening in the beginning, we learn very quickly the deflection and the movement of a structural steel or concrete slab building with infill studs is a lot more alive than in Europe. And what we started seeing is these panels are warping and cracking, and they're failing because the building is way too active. So bottom line, we came up with this system where we use clips spaced approximately 4 feet apart and on every stud. And we attach this framing system to the studs that is very, capable of moving up and down, expanding, contracting. It deals with slab edge, perimeter roof beam, deflection points, etc. So since we've actually developed this system 11 years ago, when it's being followed, we've not had a single failure in terms of panel cracking or warping or bending. When it's not being followed, we see lots of failures. So the reason we're here ultimately is we want this entire industry we operate out of Vancouver, Toronto, and everywhere in between, also on the West Coast or East Coast. We want to see this done right, and it's really so we can grow this whole industry. And there's more than enough work for competition, like Andrew over there. And anyone else who wants to bring a panel responsibly to the market, we'll approach them and say, just do it right. Don't come here, put something out there without any guidance, showing some European standard, and then have a failure, because a failure is bad for us, it's bad for the industry. So I won't talk too much longer. We'll have Mr. Kerr here do his presentation. I'd ask that you guys hold your questions to the end, because once he gets rolling, if you interrupt him, it's game over. Okay? So thank you very much for being here. This is Jeffrey Kerr.
I thought this was an apropos shot to begin with. Someone asked me at one point, it's like, so these facades for the future that you're talking about, what is it about them? What's different about them than a facade from yesteryear or anything like that? And I thought to myself, how do I explain this in sort of layperson's terms? I thought, it's a lot like cars that we used to make and cars we make now, are made very differently. And there were some advantages of the ones back then, and there's some advantages of the ones now, but the point is that they've changed a lot, they've evolved. And we made cars a lot tougher back then. So they were built a lot tougher with, in some cases, materials with a little bit more structural integrity. But when we had an accident or something like that, a collision, the car didn't do a whole lot to absorb the forces that were being transferred through the vehicle. So in some cases, they just got transferred to us. And we could be like an egg sitting in a really solid cage, and we get shaken around. Well, cars aren't like that anymore. Actually, they have things like crumple zones and airbags. So we've replaced some of this toughness with clever engineering, okay, with some smart solutions to get around some of the things, forces that maybe were significantly above and beyond the forces that the automobile was made for. Well, how does this relate to facades? Well, amazingly enough, we don't make facades anymore with a meter thick of natural stone or anything like that, and they're not necessarily made as big and bulky and maybe without as much mass and as much weight. But we're making them with lighter weight because they have to respond to some of the forces of nature, which clearly buildings are no match for when you consider things like seismic forces, et cetera, but also wind loads and what have you. So we're starting to make buildings now which give a little bit more. We're seeing wood frame construction as a really sensible solution for seismic areas because the system strength of a wood structure is really good. It gives a little and it comes back, and we can divide the load, the pressures that it's facing, amongst many members, which all have very similar characteristics to each other in terms of expansion, contraction, flexibility. So we've replaced that building things big and strong and heavy in terms of building things a little bit more intelligently, and part of that is to respond to environment, because we need to be a little bit more environmentally conscious now. So we're building with more sustainable materials, which are lighter weight, less mass. And cars from back then certainly weren't very environmentally sensitive, but they've had to become a lot more environmentally sensitive now. So there's sort of a similarity there. So moving from that picture into this discussion on facades for the future, we're going to look at some facade principles to carry us into successful solutions for the future in 3 chapters, essentially. We're going to look at sustainability, okay, low embodied energy in terms of facade materials and the characteristics that go along with those. We're going to look at higher thermal performance because, well, of course, with all the building codes that are changing in Canada, and for all intents and purposes across the world, we need better thermal performance. We need higher performance out of our buildings. And then lastly, and this was sort of the thing that kicked off everything for me, was climate change. Climate change is promising more extreme weather and a higher frequency of it. And this presentation isn't here to debate the validity of whether climate change is real or not, but if we go with the premise that it is real, and we are going to see higher frequencies of extreme weather, then I wonder how our buildings are going to react to that, seeing as how our facades are sort of on the leading edge, some of the front lines. They're going to get everything first, the effect of heat waves, higher winds, jumps over and above the freeze-thaw line. That whole substructure and these materials are going to get it really badly. So, chapter 1, materials, sustainable materials. So when we look at some of the sustainable materials for facade systems, some of the skins we'll call them, we look at things with lower embodied energy. Now, lower embodied energy can be divided into 2 areas, actually. It can be divided into initial and recurring. And initial embodied energy is the energy it takes to manufacture a particular product, to fabricate it, and for all intents and purposes to get it where we need it. Whereas the recurring energy is the energy it takes to maintain something and or replace it if it doesn't last. So interestingly enough, when we're looking at things like environmentally sustainable materials, we're looking at low embodied energy, and we're looking at materials that need to be durable, which could be very challenging when we get to reducing the weight and the mass of these materials, because generally that's what lower embodied energy is going to mean for a lot of these things, is lighter weight and lower mass. And the substructure is going to be very much the same as well. It's got to be built for these types of products, so it's got to have similar characteristics. So we've got something there, and when we get into lighter weight and lower mass, we introduce traditionally some issues in terms of expansion contraction, which are greater than higher mass, higher weight materials. And we're going to see that towards the end of the presentation, how that comes into play. So when we look at materials with lower embodied energy, we've got a few solutions here for facade skins. We've got fiber cements, high density fiber cements. We need high density specifically because we need this stuff to last, and we can't be maintaining it because we're losing energy there. We're also looking at phenolics, ceramics, porcelains, some metals, and of course the substructure to go along with that. So for engineered assemblies, for our company, we carry a variety of materials. Something like Equitone, which is essentially the grandfather of fiber cement, been around for about 118 years now. They're doing quite an incredible amount in terms of sustainability and lower embodied energy for their materials. They've taken thousands of trucks off the road in favor of moving products and materials through waterways, waste reused, water reused. And the amazing thing about some of these materials is we're not losing anything from an aesthetic standpoint. We can still make create edgy design, edgy architecture with historical relevance in some cases. So we don't really have to trade off a whole lot in terms of aesthetics for these lower embodied energy materials, more sustainable materials. And then products like Vivix, which are a phenolic core system, like I mentioned. Vivix is the exterior arm of Formica. Most people are familiar with Formica. So they know a thing or two about high pressure laminates. I don't think we could teach them anything. But that's a material which is largely, in many respects, paper-based in terms of phenolic, because you've got craft paper and resins. So the craft paper is originating, of course, in forestry. They've got forestry management systems, ISO standards. And of course, Vivix are allowing people to create contemporary architecture and build a very robust product which has that great component in terms of recurring embodied energy. And then products like Parklex, which is a real wood veneer phenolic system. So we know about phenolics and their relationship, as the aforementioned, in terms of forestry management. And Parklex have got ISO standards that they follow. And so responsible company making a real wood veneer system. So in real wood veneer, of course, we've got somewhat ironic little mixture, or we've got a real wood, but it doesn't require the maintenance. And it has a long lifespan to it, and it has a great aesthetic because being real wood, you don't need to, you don't have repeat in terms of panels, in terms of design, grain, and what have you. So you can do some great stuff, which would be identified typically as wood, but it has a lot more lifespan to it. So these are a few examples of the companies. With some of our system partners here in the crowd, they have some products as well. There's a lot of products out there to choose from, which would do great things in terms of lower embodied energy facade skins. And one of the things among a few that these systems, these materials, these companies have in common is the fact that they can all be incorporated in an RVRS system, so rear ventilated rain screen. Now the System 2 is a new system by Engineers Assemblies that we've brought out. We've been working on this progressively for years. So we've come out with System 2. And the rear ventilated rain screen system here, as we identify it, is something that all those materials can share in. Now, it's important to note that rain screens aren't new. Of course, they've been around since the 50s easily. And there are probably as many definitions for rain screen as there are for free-range chickens. So to be more specific about the rain screen we're talking about here, it's not a rain screen where we have a 10-millimeter gap for water to make its way down in the envelope system, gravity assisted. We're talking about a lot of ventilation. The RVRS system that we talk about is based on DIN standard 18516, which is a standard known as ventilated facade. And it's a rain screen system which puts a lot of emphasis on ventilation. Okay, so ventilation, good. Water, bad when it comes to envelopes anyways. So when we look at this system here, we've got a facade skin in the red, okay? And then we've got a vertical hat bar channel, which is 25 millimeters deep, giving us a 25 millimeter active plenum. So we've got a ventilation cavity, uninterrupted, of 25 millimeters. Now, that dimension can change depending on how high you're going up in the building, but it's never less than 25 millimeters. So we've got a good ventilation chamber there, chimney effect, and just behind that we've got a weather membrane that we use when we've got open joint systems out front, like many of these panels use. And that weather membrane is going to sit in front of the insulation. It's going to protect the insulation. It's going to protect it from a few things. One, it's acting as a drainage plane. It's continuous along the insulation. So any moisture, direct precipitation that comes through the open joint system hits that plane and goes down. Okay? Now, that membrane, we employ a product called SRP Air Out Shield. It's essentially Gore-Tex for a building. It breathes unidirectionally, high perm rate, but you could open a head of water on it. So open a hose on it, and it won't let moisture through. Now, We also use a UV stable system. So you can use any insulation within this type of model. So you're using spray foam. Spray foam's not UV stable. No problem. The membrane's UV stable, protects the insulation. Using something like mineral wool. Mineral wool can absorb moisture. We don't necessarily want to see the green. Well, the membrane's black, so it creates a black backdrop. It's a shadow effect and prevents moisture from soaking the insulation. Now, many mineral wools manufacturers will contend our mineral wool can handle moisture, and it can. But dry insulation works better than wet insulation, we know. And if we can keep that cavity in there, that plane where that horizontal gird is that we see there, that plane of the insulation, we can keep that area dry, it'll be better for the substructure. The substructure will last a lot longer. So we've got that horizontal gird system in there as that gird, and it's sitting on a T-clip, which is an engineered Assemblies thermally broken clip system. So we've got a thermally broken substructure, which is essentially going to give us higher effective R values, and we'll get into that. We've got a thermally broken substructure and a whole lot of ventilation, and it's a lightweight, outboard insulated, continuous insulation system, which a lot of our codes are requiring for these days, continuous insulation. So we can get great performance out of our insulation, and we can fulfill the requirements of the code. So this is something I wanted to bring up in terms of that whole ventilation cavity and the importance of that. I was speaking to an engineer recently, and we were talking about the ventilation cavity, et cetera, in the active plenum, and he said, oh, like the microclimate. I was like, talk to me about this. He said, well, it's essentially like a microclimate what you've got in there, because ultimately you've got this plenum of air, you've got this air moving through that cavity continually. So if we're looking at a building in July, let's say, where we've got 28 degrees Celsius outside and the sun's beating down on it, we've got a whole lot of solar heat gain coming down on that panel. So we've got all this excessive heat. Well, here in July, we would want to have the interior of the building maybe sitting around 20 degrees in a more comfortable environment. We've got a whole bunch of heat coming on that's challenging the climate inside the building. We've got this venting plenum of moving air that's dissipating some of the heat off the panel system, so it isn't going to continue through the envelope. And Morrison Hirschfield, through a bunch of work, said, you know what? We found that you can get 0.7 of an R value in that 25 millimeters of air. So actually get some insulation value out of that air pocket. So we got this little climate, which is a different temperature than the inside portion of the envelope, different temperature than the inside of the building, certainly a different temperature from the outside, and it's benefiting from a thermal standpoint, it's benefiting obviously from a ventilation standpoint, because this volume of air moving through the cavity, which is open at the top, open at the bottom, protected by a 50% perforated aluminum screen. We'll call it a bird and bat screen, so we don't get friends living in our envelope. And it creates a vacuum. So we've got a small vacuum in there, pulling, pulling, pulling. Well, we know that direct precipitation isn't going to get through our membrane, but we're going to get condensation, because in this particular model here, we're going to have a dew point. Probably going to sit around here. We're going to have condensation develop in our insulation. So we need to dry that out. And people are always concerned about, well, if you've got moisture in there, what's going to happen to your substructure? So, well, there might be a little bit of moisture in there, but we've got really good ventilation. So what do we do in the basement when we get water in the basement, floods the rug? Well, lift it up and put it on a couple of chairs, turn on a fan. Best way to get rid of it. We can't just rely on gravity to get this stuff down. But as I say, this isn't something that we created. This is based on a very old European DIN standard, which is very well proven and documented, created by engineering. So when we're looking at stuff like this is obviously not an old way, so to speak. We're told that old ways don't work, and I think what they're referring to is not all the old ways, but old ways in terms of the way we used to insulate buildings, the way we used to build buildings. And we know from a thermal performance specifically, old ways don't work as well as the new ways. And the building codes are demanding that we build a little bit better. So we mentioned before about thermally broken substructure and higher effective R value. Well, for those who aren't as familiar with it, the effective R value is essentially the R value of a system of insulation, but of a system, after we take all the inefficiencies out. Because we're going to have inefficiencies in a system. When we've got insulation, let's say a bat of mineral wool, and it's 5 inches, we're going to have an effective R value that is a little bit different than the value that's written on the bag, so to speak. So we might see that it's written as R21, but when we put it into an envelope like this, we got metal running through it, we got a whole bunch of things. What's the effective, what's the real R value after we put it in place? That's something different. And that's what the codes are requiring us. Build to R, effective R24, they'll say on the wall. So, walls. Walls are important. So chapter 2, thermal performance. We just looked at facade systems and facade materials, but onto thermal performance. We've got people like ASHRAE, the American Society for Heating, Refrigeration, and Air Conditioning Engineers, and people like Morrison Hershfield and RDH and RJC, and a lot of these people are doing work with matters thermal, and they're saying, okay, we know we've got some inefficiencies in the system. We know that walls are important. We used to think roofs were really important because heat would rise in the winter, heating our building. We got to insulate the roof really well, but how about the walls? Well, we can lose an exceptional amount of energy through the walls, and buildings use an exceptional amount of energy. So in the interest of doing something more environmentally friendly, we need to amp up the performance in the walls. And by that, we need to eliminate the heat bypass. So people got together and said, there's heat bypass going on, we're losing energy. How much are we losing? Well, when we thermally break something, we can separate these environments that we're running heat energy into, and these environments that we don't want to run heat energy into. And through that thermographic image, we can see, okay, blue cold, red hot, or red warm. And we want to separate them, keep them very distinct. And we do that with a thermally broken substructure. Now, Engineer Assemblies created something called a System 2 design guide. And we've created a design guide for years, and John started that a long time ago. And it detailed just about every condition that would happen on a building vis-a-vis envelopes. But it's very prescriptive now. It shows people step by step a whole bunch of important information on thermally broken substructures and how to lay out substructures for rear ventilated rain screens, which are very, very effective in our market. And it includes things like tables like this. So this is a table. We have a variety of tables like this in our System 2 design guide. And this one is created by Morrison Hershfield. So we had third-party engineering do all of this work for us. And they came back and we were talking about that thing about nominal insulation value on the bag and 5 inches. Well, that 5 inches of mineral wool, 5 inches, nominal value 21. That's what we start off with before we interrupt it, before we intrude into it with metal components and substructure. We go over into the far side, okay? So on the right-hand side, into the old ways, when we're just running metal through it without it being thermally broken, we're ending up with R11 to R15. Well, R11 represents about 55% of this value. So we're throwing out 45% of the insulation value by not thermally breaking it. And then 15 is a really complicated way to cross-gird, et cetera, and we still only get 70%, so 30% out the door. But yet when we go into a thermally broken system like the EAT clip system, a good thermally broken system, and not just a clip. Well, these clips do not perform amazing on their own. They have to be a part of a whole system, so we have to measure it as a whole. When we measure it as a whole, we get things like R values from 19 to 21. We got 21.4, actually. Now, it's a little bit higher than this, and we know that Morrison Hershfield suggested, well, we can find R0.7 in that pocket of air you have. And there's a bunch of other little materials along the way which have some insulation factors. And in fact, Engineer Assemblies, doing the R&D of this kind of stuff over the years, we've got breakdowns of every single component in an envelope, whether it gives or takes in terms of performance. So you can take a look at an envelope and examine exactly what it's doing, how it should be performing. So these tables in the design guide's free. Download it off our website, engineersassemblies.com. As John suggested, sharing works. We want to try to make the industry better. We want to grow the pie for everybody. It just goes without saying, as a business plan, if we can make the pie bigger, our piece will probably get bigger. At somewhere along the line, there's a business opportunity here, but the biggest opportunity, I think, is for us to build great, brilliant buildings, which perform really well. And part of trying to get them to perform really well is addressing some of the complications that we have with these types of systems. So we go into chapter 3, dynamics of facades. This chapter can probably be summarized best by substructures, superstructures, expansion, contraction, movement. That is inevitable. It's going to happen. How do we deal with it? How do we deal with it with a particular type of facade system? So in terms of a facade for the future, we need a facade that uses low embodied energy, sustainable materials as a skin. We need high thermal performance. And we need things that stand up and last, and are going to stand up and last to some of the unfortunate news that will be handed to us in terms of extreme weather and higher frequency of that. So, design guide, answers, not all of them. This whole thing began for me thinking about this presentation as, I got 1,000 questions. And I probably still have a whole mess of questions after this. And I think the answers start with us figuring out what are all the questions. So Engineers Assemblies figured out a lot of them with the help of the engineering community and architectural community. But we still have a lot of questions, and we need your help. You're all partners in this, to figure out what kind of questions we need to ask in terms of making a successful system for the future. 7 factors for future-ready facades. This is something that we mentioned in the guide right up front. This is something that John wanted right up front when this new system got introduced, was what are the fundamental principles that are non-negotiable for our system, for a good system to work. And those include things like we just mentioned, coefficient of movement, expansion, contraction, movement of buildings, substructures, materials. We need great ventilation. We need a great strong substructure to support these materials, because these materials, you can't just flex them and bend them all the time. So it needs to be solid in some planes. And ultimately, we need systems like the Engineers Assemblies T-clip is adjustable for subwall misalignment. That's a performance issue, because ultimately our buildings in North America are not built straight all the time, and we certainly get involved in retrofits where buildings aren't straight, so we need to be able to make them straight. So adjustability. So these are some of the features, and the guidance is here in guides like that and other resources that we have in the industry. So when we're looking at things like the expansion, contraction, and movement of buildings, we get into certain details where it's probably best explained if I said, we take a facade on a building. If it was a building that was about the shape of this screen, we would divide the facade into quadrants. And by that I mean, we don't just put a substructure to hold the facade. We don't just put a substructure up that casts a big heavy metal net over top of the whole building, like a cage. Because the substructure is going to move, the panels want to move, panels want to expand and contract, the superstructure is going to move. That's why we put control joints in buildings. Things are going to move around. And if we try to harness it down with some lightweight substructure, something's going to give. It's probably not going to be the superstructure. So if we divide it into quadrants, if we said, well, we'll make 3 quadrants high and 3 quadrants across, we'd have 9 quadrants, let's say. Well, we know, engineers have told us, well, wind loads are higher at the corners than they are in the center. Okay, so we're going to have more forces in the corners, okay. There's a bunch of other factors in terms of heat and expansion, contraction. We can separate the substructure. Well, we know for starters, we take a building like we build here in Canada with a slab edge, concrete slab edge. Those are points of deflection. So our vertical hat bars that we suggested in the rear ventilated rain screen system, the vertical hat bars that are creating our active plenum space, those can't cross over. Those can't cross over the slab edges. They have to stop and start every slab edge. And they can be separated by as little as 3 millimeters. But we need to separate them every slab edge. And then the horizontal Z bars that are running along the clips in the insulation plane, those can run 3 meters, separate, 3 meters, separate. We've still got amazing system strength in each quadrant, but the quadrants can move because we're going to see movement. We're going to see increased wind loads and expansion, contraction, overheat differentials. So this is an important point. It's a really simple point to make, and I think everybody understands points of deflection in a building and not trying to cast a big lightweight metal net around it. And when I say lightweight, I mean in relation to the forces that are being exerted against it. But we have control joints. I think that's pretty much a no-brainer. Control joints are there for a reason because we expect the building to move there. And we can't cross our substructure over that. And this comes to light because, well, one, there are certain fundamental principles that we know about construction that we would know to do something like this, but it also comes to light because, amazingly enough, in our travels, John and I have seen failures on products. And when we've raised the question to some of the people, and in some case, it was some aspects of engineering or just of the people in the construction industry who said, well, you're separating your substructure, right? It's like it's divided. You're not trying to tie the whole building up, right, and lock it down with 18 gauge. But they are. We'd see hat bars 25 feet long, stitched together, running up the whole building, right across all the points of deflection of the slab edges. And we'd see substructure running right across control joint areas and things like that. And so materials fail, and it's because we're not respecting some of these things. So amazingly enough, just as an aside, we need to develop designs, et cetera, to address these kinds of things, but we need them carried out. We need them carried out in the construction industry. We need people to understand, be educated. This is what buildings do. And maybe people are explaining and people aren't listening well enough, but we need to make sure that happens. So when we look at adjustability, we talked about adjustability for subwall misalignment. That's something that the T-clip does. That's real. Buildings aren't straight, but we need to straighten the facade out for aesthetic reasons more than anything. And in terms of flexibility, years ago when we were developing the design guide, the engineering people we were working with said, when we asked, well, the 3 millimeters between things, is that enough? Like, are things going to move more than 3 mil? It's like, they can. And if they do move more than 3 mil, then the way we've designed the system, things can flex. Things can run into each other and flex a little bit. It won't result in snapping, but we need to have some initial separation. So there's some flexibility within the substructure, and then we've got to divide it into quadrants. So we're on the road to doing the right thing. We're doing all the right things. Probably some more answers out there that we need. And then when we get into materials, when we suspend the materials on these substructures, which have a little bit of play in them for good reason, we need to make sure we have fixed and floating points on all the panels. That means, so the dark points on this panel are fixed. And all the other points are floaters. We've got room between the fastening system and the hole drilled out through the panel. A little bit of float, a few millimeters. Doesn't seem like much, but try to compress a piece of glass a few millimeters and see what happens. Eventually, things are going to give. So we got flow to the panel, which actually helps us with a little bit of flow to the substructure. And remember, the substructure and the panels are lightweight, lower mass. That's what we're moving with. They're going to expand and contract more. So we need things like this. And been a part of approximately 1,000 projects now from C to C. And when this model is followed, we don't have failures. So we could suggest that the model doesn't need to be followed, but there are failures in that model. So following this just seems like a fairly common sense route to go. And it's not unaffordable. We're talking about very small percentages over the cheapest, simplest, non-performing method to construct, okay? But failures are inevitable, and when we see failures, we generally can point to some pretty simple things. Ventilation, expansion, contraction. That's usually the biggest problem with facade systems. And we see metal panels, and we've spoken to people in the industry, because Engineer Assemblies doesn't do ACM or anything like that. But we've spoken to our partners in the ACM industry and said, oh yeah, we've had panels tear, rivets pop their heads off. We've had problems like that at corners, various points. Like, we're not leaving room for the materials to do what they naturally want to do in some circumstances. So just tying things up here, an interferometric synthetic aperture radar. It's an interesting little device. It's not an app on a phone yet, but it's an interesting animal. And I came across this because I was speaking to some geologists, some really great geologists who were working, or Canadian people, but they're working at the University of South Florida, and they do a lot of work in Greenland and with ice fields. And I was asking them, like, what can you tell me about climate change and what's it going to do and la, la, la. And we got talking about it. I was like, can you send me some stuff? And he said, oh, this might interest you. This is an interferometric synthetic aperture radar. Here's a PowerPoint presentation on some stuff we did with it. I'm like, what do you do with this thing? Like, well, we pointed at glaciers, and we can see how glaciers move. And we used to just drive a stake in the ground and say, well, the glacier was here last May. Now it's here. So it moved 10 inches or whatever. It really doesn't tell us how the glacier moved. But an interferometric synthetic aperture radar does tell us, gives us an idea of displacement. How did it move over what period of time? And when they were figuring this stuff out, they started working with this thing more and more, and they would fire it at a bridge, and they could say, oh, when the trucks go over, the bridge deflects so much over such a period of time. And then they got one up in a satellite. And they were firing it down on a building, this building, in 2010 in El Paso, USA, and it was in a heat wave. And they measured the building grew multiple centimeters in the heat wave. And they're like, what? Well, that's an amazing thing. I mentioned it to a few people. They're like, wow, that's crazy. It's like, yeah, heat causes things to expand, things grow. What's the radar really measuring on this? Probably not measuring the superstructure. It's just measuring the outside, the facade system. The facade system's lighter weight. It's growing and coming back down when the temperature comes back down. Well, if we're seeing that much movement, is everything moving in concert with it? Are there allowances for everything to move like that? Probably not, or we wouldn't be seeing the failures that we see. So we got a lot of movement and a lot of potential movement, and we're promised a lot more movement in the extreme weather and higher frequency of that through climate change. So we've got real examples like this with real science showing us that this stuff happens, and so this is a question that we should be addressing. And just like cars of yesteryear, when we started looking into, wow, maybe the environment isn't getting the fair shake here with all the emissions and fuel, et cetera, that we're using with these big old heavy cars, we should start making more fuel efficient machines. Well, and it became a conversation people would have at the kitchen table or in living rooms. And now something like Time magazine comes around and dumps this on the coffee tables of our homes and says, now the discussion of climate change in architecture has become something public. I don't think it all falls on the shoulders of architects, but rather engineers and other various scientists, and figure out, how do we need to build differently for climate change? And I know people have thought about it, but what are we doing about it in terms of facades, which are on the front lines of a building. So I think the first step is we've always believed in a very strong conversation between, or rather a mutual language between the house of design and the field of construction. Get those things together so people can speak well to each other and be understood. But we also need to take into consideration now environmental sustainability of materials and climate change and the promises that it has for us. And we bring all those four things together, and these things can all work very easily together. And we've got a lot of answers, but we probably don't have all of them, and there's probably a lot of good questions to ask. But this is a really good start, And so with that in mind, I'd like to thank you for spending this time with us talking about this subject. We're Engineered Assemblies. We have a booth here at 1150, but go to our website, download our System 2 Design Guide. It's got a lot of good information in it, and we welcome questions, not only through email, etc., but we welcome questions now. So thank you very much.